Hi everyone, welcome back to the series on radar imaging. In this video, I'm going to talk about a new set of algorithms for 3D SAR imaging. I'll focus on FMCW. So let's begin. So this is the 6th video, I believe, in the series. 7th video. So I'll call it range migration algorithm. That's what it's called. There are other names for it, which we'll talk about. So what is this for? This is for fast 3D. Here we'll cover SAR imaging, but you can also use it for MIMO, which we'll cover in another video. Okay. So maybe first let's do a quick review of what we've covered so far. So we started with a series on FMCW radars, step frequency radars, pulse radars. So we did 3 videos on these, covering the signal processing aspects of each. And we developed a generalized signal model for all of them. Okay, this was actually developed in the SAR video, which is what I'm going to talk about next. Okay, so then we made a video on 3D SAR imaging, SAR reconstruction using back projection or time domain correlation. And we also talked about MIMO radar and how to reconstruct using back projection for MIMO. Okay, the third part of the series was on FMCW SAR imaging using HFSS and MATLAB. Okay, and today the fourth part is we will discuss fast 3D SAR imaging and use experimental data to form some real world images. For real world 3D imaging. Okay, so I'll do this in 2 parts. In the first part, I'll cover the fast 3D imaging algorithm. And in the second part, we'll look at the experimental data, how to process that data and form really high quality 3D images. Okay, so that's sort of the review. 7.1 is let's motivate why we need a fast algorithm / motivation. So, you may say, okay, what's the point of this since we already have back projection and time domain correlation? Why do we need something else for 3D SAR reconstruction or 3D SAR imaging? And the answer to that is if you want to do high resolution millimeter wave imaging, then back projection is actually very slow. So let's take an example, right? The best way to learn is, in my opinion, through examples. So let's take an example. So, okay, so let's, just to recall, we saw that the back projection equation is, the reconstructed image F tilde is a triple summation over K. This should actually be KT or T time over KT over X prime over Y prime. Sorry, not K. This should be over just K. Okay. This was the measured result, the measured data, X prime, Y prime, K. And we have here e to the 2jk. This is the phase compensation part. X minus X prime square plus Y minus Y prime square plus Z squared. right? So if you don't know what this is, then I suggest going back and looking at the SAR reconstruction video where we derived this. Okay, so let's assume I have n by n by n points. So my, my grid that I'm measuring over has n points in X, n points in Y, and I have n time samples as well, right? So then for each pixel, you have to do n cube computations, multiplications and summations. And then we have, let's assume, just for simplicity, n by n by n pixels, right? So you're forming a 3D image over n cube space, and you have measured data over n cube variables, right? Which means that the total amount of computation you need to do is on the order of n to the 6, right? So that's large. So if you take an example, so let's say you want to simulate an image or form an image that has, I don't know, 251 by 251 pixels. So this image quality will be around 62.5 kilopixels. That's not much, really. We usually deal with megapixels when it comes to real imaging, but let's say for radar, this is enough. So 251 by 251, and let's say we have about time samples, I'll call it NT, equal to 2400. The reason I'm taking these specific numbers is because the experimental data we deal with later has these variables set to these values. Okay. So what's the total number of computations? That is 251 to the power of 4 times 2400 to the power of 2, right? Because this is NT and NT here. And this comes out to approximately 10 to the 16. So let's say, you're using an 8 gigahertz computer, which is approximately able to do around 10 to the 9 computations. Not exactly computations, but let's assume, okay, it can do around 10 to the 9 of these computations, multiplications and additions per second, which is somewhat reasonable. Then you have to do 10 to the 16 computations. You're doing 10 to the 9 per second, which means that you have about 10 to the 7 seconds to compute all of this, right? And that's about approximately 115 days. So on a standard desktop computer, if you just use this equation and you implement it perfectly without any for loops, nothing, right? This would be about 115 days. Now, in a realistic simulation or reconstruction, let's say using MATLAB, which is what I've done, it works out to about 3,500 days. So if you do this in MATLAB, just I obviously didn't run it for 3,500 days. I just computed it for one pixel. And if you do it for all pixels, that would work out to about approximately 10 years, right? So obviously we don't want to sit around for 10 years until we form an image. But even if you implement it in C++, still is not fast enough, right? So in today's video, we're going to see how we can reduce the computation time from 3,500 days to about 40 seconds. And that's a huge, huge improvement, of course. Okay, so what's the idea, right? So the idea is that if you go back and look at this equation, this exponential term that this is multiplied with kind of looks like a Fourier transform. Fourier transform, right? And we know that if we have a Fourier transform and everything is uniformly sampled, then we can use an FFT to speed things up a lot more. So that's the idea. So it's not exactly a Fourier transform, so we have to massage this a little bit, and that's what the algorithm really does, which we'll derive. Okay. So what is the algorithm called? It has different names. So the first name is, because it was kind of rediscovered by different people in different areas. It's used in tomography, it's used in radar, it's used in sonar, it's used in topography mapping, geoscience, things like that as well. So That's why it has so many names. So it's called range migration algorithm or frequency wave number algorithm. Omega K, it's also known as Omega K algorithm. Another name is holographic reconstruction. So the derivation of holographic reconstruction is different from range migration, but the final reconstruction algorithm itself is the same. Okay, so I'll leave some references in the description. To some papers that have talked about these algorithms in more detail. I'll focus on like 3D SAR. Of course, this work's also been done in 2D SAR very extensively, but I'll focus on the 3D SAR imaging. So you check out the references if you're interested. Okay, so let's get started on the algorithm itself. So we'll start with the signal model, as always. Okay, so if you don't know what this is, then go back and look at the FMCW or the pulse, step frequency, SAR reconstruction videos. We've covered what signal models are over there. So I'm just going to assume you watch those videos or you're already familiar with this. So, okay. So we can write the received signal at position x prime, y prime, and time t or kt. I guess I'll talk about what kt is, but this is what we derived earlier for FMCW SAR. Is a triple integral over space over x, y, z. The reflectivity function f of x, y, z times e to the minus 2j kt modulus of r minus r prime, which we also called as r, divided by 16 pi square r square dx dy dz. Right? So essentially what this is saying is that if I have some target and I have my radar here measuring over this plane, then you look at the reflectivity at each point, and then the two-way propagation gives you this two-way propagation phase. And this is the spherical wave. The spherical wave function, which decreases over time as 1 over r. And since it's two-way, it's 1 over r squared. 1 over 4 pi r and 1 over 4 pi r for each, for the transmission and then the reflection. You can go back and look at that video to review where this comes from. And kt we derive for FMCW is omega c plus beta t over c, where beta is the chirp rate. So kt and t are kind of, there's an equivalence relation between the two of them, right? Which is the bandwidth over the chirp duration. And t belongs to minus tp over 2 to tp over tp is the chirp duration. I think I called it ts earlier, but let's just call it tp for now. Okay, and then r is modulus of r minus r prime, which is square root of x minus x prime square plus y minus y prime square plus z minus z prime square. But here we assume the coordinate system to be such that z prime is 0. Okay, so that's the signal model, 7.2. So we look at two different solutions to the signal model, 7.3 I'll call it. So first we look at the holographic reconstruction. So this is one derivation. So the whole point of imaging is to invert this expression to get f from the measured SB, right? So we have SB in terms of f, but we want to invert this equation so we can write f in terms of SB, right? So that's what we're trying to derive now. How do you go from one to the other? Sorry. Okay, so let's start that. It's not that difficult. So we start with something called the while identity, e to the minus I k t r over r, or the plane wave expansion. This is a mathematical identity. I'm not going to prove it, but you can find it in books. Kx prime, ky prime, e to the minus j kx prime, x minus x prime, minus j ky prime, y minus y prime, minus j kz z over kz. And then there's a d kx prime, dky prime. So what this is saying is, it's called plane wave expansion as well. So what this is saying is that this is a spherical wave, right? Spherical phase front. And these are all plane waves in some direction given by k prime, which is kx prime x hat plus ky prime y hat plus kz z hat, right? So what this is saying is you can write a spherical wave as a summation of an infinite number of plane waves in all directions, right? So that's what these integrals are doing. So we'll use this expansion. So I'll call this, this is called the while identity. And on the right-hand side, we haven't defined what this kz is. The while identity itself defines it as kz is equal to square root of 4 kt squared minus kx prime squared minus ky prime squared. The factor of 4 actually comes from 2 here. So I should say 2 ktr. Yeah. So since in our case we have 2 ktr, that's why I'm using 2. If it was just ktr, then this factor of 4 would not be there. Okay. So we have this identity. Now what we're going to do is we have exactly the same term here, right? E to the minus j ktr, or 2j ktr, and there's a 1 over r term as well. So we'll plug this in to the back project or the signal model that we developed. So what happens when you do that? Then we're left with SB x prime y prime kt is equal to minus j over 2 pi. We have the triple integral xy z f of xyz over 16 pi square r, and now the double integral kx prime ky prime e to the minus j kx prime x minus x prime minus j ky prime y minus y prime minus j kz z over kz. And then we're left with dkx prime, dky prime, dx, dy, dz. Right, so it looks very complicated, but it's not really that complicated. Okay, so one thing that people usually do at this point is to say that which is a practical thing to do, is an approximation which says that basically any slowly varying functions here don't affect the reconstruction much. So for example, this is a constant that doesn't matter, right? 1 over r is a slowly varying function, so that doesn't matter. So we'll just replace all of these slowly varying functions with 1. Okay, that makes it easier. Why slowly varying functions don't affect the reconstruction? Most of the reconstruction is captured by this phase. That's true in imaging in general, is that when you have a slowly varying function, it doesn't really change the reconstruction as much. Proving it rigorously requires a lot more effort, so just take it for now that that's the case. Okay, so once we make these approximations, then this becomes equal to, so now we rearrange the integral. So I'll pull this integral in there and then pull this out here. Since x, y, z, k, x prime, k, y prime are not dependent on each other. You can kind of move things around. So we're left with kx prime, ky prime, e to the j, kx prime, x prime, plus j, ky prime, y prime. And then we have a triple integral x, y, z. Of x, y, z, e to the minus j, kx prime x, minus j, ky prime y, minus j, kzz, dx, dy, dz, times dkx prime, dky prime. Okay. And another thing to note is that let's assume, actually, this is an assumption. It's not exactly an assumption, it's more like an imposition. So we assume that coordinate system, systems in x and y are the same, or I should say coordinate system x comma y is the same as x prime, y prime. So what does that mean? That means that if I, take my data over a grid, some grid, then the image would also form in exactly the same grid in x and y. Of course, the z will be different. You can change the z. You can form the image in different locations in z, but in x and y, it's the same. So with this assumption, basically what we can do is we can say that, we can drop the prime coordinates in x and y. It's the same thing as kx, ky, right? So then what happens? If we do that, then this is nothing but the Fourier transform of f of x comma y comma z. And this is the inverse Fourier transform of the Fourier transform of f of x comma y comma z, right? And that should be pretty obvious if you know what the Fourier transform is, that that's the case. Okay, so let's write that again. So SB of x prime comma y prime comma kt is nothing but the 2D inverse Fourier transform of the 3D Fourier transform of f of x comma y comma z. Okay, and of course, once we have this, we can invert this and say that f of x comma y comma z is equal to the 3D inverse Fourier transform of the 2D Fourier transform of the measured signal y prime. I mean, this may look simple enough, and you may say, okay, well, what's the point of taking Fourier transform and then again inverse Fourier transform? It's like doing nothing, but that's not the case actually, and we'll see why. There's a step in the middle that we need to do. Okay, so this is actually pretty straightforward, right? Because now x prime and y prime are assumed to be on a uniform grid of measurements, right? So the spacing is all, it has to be uniform in x and y, right? Then you can just simply apply FFT to this, right? So then that would just be 3D. No, I'm just going to say FFT or 2D of SB x prime comma y prime comma kt, assuming x prime and y prime are on a uniform grid. Okay, so then I'll call that capital SB of kx prime, ky prime, comma kt, right? But now there's a problem. Now we want to take a 3D inverse Fourier transform, but kx prime, ky prime, kt are not on a uniform grid. Why? Right? Kx prime and ky prime are, but kt is not kz, right? It's something else. There's a relationship that it shares with kz, but it's not. So what's the relationship? If we go back earlier, I said that along with the Weil identity, there's this. Let's go back. So there is this dispersion relation, which relates kz to kt, right? So we said kz is equal to square root of 4 kt square minus kx prime square minus ky prime square, right? And kt is uniformly sampled. So kt is uniformly sampled because t is uniformly sampled. Right? And we said that kt is omega c plus beta t over c. So if t is uniformly sampled, then k is also uniformly, kt is uniformly sampled. But this equation is not a linear equation with respect to kt. So kz is actually not uniformly sampled. So we need to kind of resample it. So what do I mean by that? So let's draw a figure to illustrate what I'm saying. So let's assume this is the k space. We'll have kx, ky. You can call it kx prime, ky prime, whatever. Doesn't matter because it's the same as kx, ky. So ideally, you want your data, which is now in Fourier space, SB, capital SB, to be on a uniform grid, right? So it should be sampled on this uniform grid. But we know that that's not the case, right? Because what we have actually is that kx prime plus square plus ky prime square plus kz prime or kz square is equal to 4kt square, right? Which means that for a given kx prime, ky prime, kz lies on this on spheres. What kind of spheres? So it's something like this. Right? So, I mean, I can only draw it in 2D, of course, but since kx, ky are the same, just imagine this to be symmetric about the z-axis, kz axis, right? So essentially your sampling is going to be out here on these circles, something like that. So imagine taking like sheets and then projecting them onto a surface of a sphere. That's what it looks like. So your function SB, capital SB, is sampled on this non-uniform grid, which lies on these concentric spheres. And we need to resample it so that you can so that instead it lies on a uniform grid in order to apply FFT. Right, so that's what we need to do. Okay, so what do we need to do? We need to interpolate capital SB, that's on kx, ky, kt, to capital SB, that lies on kx, ky, az that are uniformly sampled. And then apply a 2D, 3D IFFT, and then take 3D IFFT. Okay, so the interpolation is really only in Z, right? So yeah, so for example, you'll have you know, since kx and ky are uniformly sampled, you'll have samples that lie like this. And the next one would be here, 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 here. So this one's corresponding sample would be there. You're not drawing that right. Let's do that again. So it's uniformly sampled in X and Y. So the next sample is there, next sample is there, next sample is there, next sample is here. This one's next sample is here, next is there, next is there. This one's is here, and so on, right? Because of that, we want to resample only in Z. So for example, we say, okay, I want to set my sampling such that in Z, it's uniformly sampled this way, which means I need to sample on these points for this line. For this line, it should be again on the same points. For the next line, it should again be on the same points, and so on. Right? So you only need to resample in Z, not in X and Y. Right? The interpolation only needs to be done for each of the Z case. And that will bring it onto a uniform grid. So this interpolation in Z in KZ is called Stolt interpolation in the literature. So if you see that name, you know what it is. Okay, so that basically completes the derivation. So the steps in the algorithm are pretty simple. You start with something that you measure on x prime, y prime, kt. You take a 2D Fourier transform, fast Fourier transform, and that gives you capital SB, kx prime, ky prime, kt. Then you do the Stolt interpolation. That gives you capital SB on kx prime, ky prime, kz. And I'm just going to drop the primes because it's the same as we discussed. And then we take a 3D IFFT to get f of xy's, right? So if you look at now, what are the order of computations? This one is of order n square log n square. It's 2D FFT. Okay, this one is order of n cubed. Actually, this one is not. This is order n cubed times log n square, I think, because you have a 2D FFT, but you also have a third dimension over which you need to calculate these 2D FFTs. So it's not a single 2D FFT, it's n 2D FFTs, right? And I may be wrong on that, but I think that's the case. And the last one is n cubed log n cubed. So overall, it's really just, the way this order system works is now the overall is just order n cubed log n cubed, right? So the same example, if we take before, 251 times 251 times 2400 times log of 251 times log 251, log base 2, of course, 2400. This is approximately 100 seconds compared to 100 to 1,000 days. That's much faster. And in MATLAB, when you implement this for the same size array, it comes out to about 40 seconds actually. Of course, we made some approximations here in this calculation. So in reality, it comes down to 40 seconds, which is very fast. C++, it would be even faster. So, okay, so that's holographic reconstruction. The next part is range migration. It's the same final result, but the derivation is different. So I'll call this range migration or omega k, same thing. Okay, so earlier what we did is we took the while identity And then we inserted it into the signal model. And then we rearranged the integrals, removed some of those constant terms, slowly varying terms. And we saw that it takes the form of the FFTs, right? So in this case, we don't use the while identity. We directly apply Fourier transform. So I'll just write out the signal model once again. XYZ, f of x comma y comma z, e to the minus 2 j k t r over 16 pi square r square dx dy dz, right? So now what we do is we take a 2D Fourier transform on both sides. With respect to x prime and y prime, right? Recall that r is x minus x prime square plus y minus y prime square plus z square. Okay, so when I take the 2D Fourier transform on the left, we get the same capital SB times kx prime, ky prime, kt, and that is equal to integral, triple integral xyz. And I'm pulling the Fourier transform integral inside because f of xyz doesn't depend on x prime and y prime. And then we have the double integral x prime y prime, which is the Fourier transform integral, e to the minus 2 j k t r over 16 pi square r square, e to the minus j k x prime minus j k y prime dx prime dy prime dx dy dz. Right, so this is exactly the Fourier transform that we applied. Okay, so now we want to evaluate this Fourier transform on the right. So I'll write that out separately. E to the minus 2 j k t r over 16 pi square r square e to the minus j k x prime minus j k y prime dx prime dy prime. The interesting thing about this expression is that it has this phase term that's very fast varying, right? And this phase term and this amplitude term that's slowly varying. So when you have an integral like this, one trick that you can use is called method of stationary phase. And I'll leave a reference in the description as to how you can use this method of stationary phase to evaluate integrals like this. But you can actually use this approximation to evaluate this integral. The idea behind stationary phase is this, is that if I have an integral of a function that's varying very fast and then becomes slow, and then again varies very fast, the region where it varies very fast has almost no contribution because it cancels itself. Whereas where it changes very slowly, where the phase is sort of stationary, what they mean by that is the derivative of the phase is zero, right? It's not changing very fast. Most of the contribution or all the contribution to the integral just comes from that region. So you can just evaluate the expression in this region, its derivatives as well, second derivative, and then you can approximate solutions to such integrals using this method. You can look at references in the description to go over it in more detail. This video would become too long if I start deriving that, so I'm going to leave it at that. An interesting thing to note actually is that this integral can also be evaluated analytically. That's much more challenging, and I'll leave a hint in the description as to how you can evaluate analytically, but you can try that as an exercise. So evaluating this will give you the following result: kt z naught e to the minus j z square root of 4 kt square minus kx prime square minus ky prime square e to the minus j kx prime x minus j ky prime y. Okay, and now you can define this to be kz. right? So then that just becomes pi j over kt z naught e to the minus j kzz minus j kx prime x minus j ky prime y. And that's very nice, right? Because now you can simply, take this whole thing and plug it in here, right? Because that's the integral we were evaluating. Okay, so let's do that and see what we get. So when you do that, you get SP, capital SP, kx prime, ky prime, kt is equal to triple integral xyz, f of xyz times pi j over kt naught e to the minus j kx prime x minus j ky prime y minus j kzz dx dy dz. And again, saying that x prime and y prime are the same in the coordinate system is the same for xy and x prime y prime. Implies that kx comma ky is the same as kx ky. So then this whole thing becomes the 3D Fourier transform of f of xyz times pi j over ktz naught, right? Now at this point, you can say, okay, slowly varying functions like kt don't affect the reconstruction. So you can just ignore this whole term, and then you end up with SB kx prime, ky prime, kt is just the 3D Fourier transform of f. But you can also actually leave it there, times pi j over kt. This should actually be z, not z naught. Go back. Yeah. Okay. That's right. Okay, which means that what? F of xyz is the same thing as kt z over pi j times, excuse me, Fourier transform 3D inverse of the Fourier transform 2D of fb x prime y prime kt, right? And I'll just ignore this to make it the same result as the other one. You can ignore that because it's slowly varying, like we spoke about, right? Okay, so of course, the same expression. So you apply the same algorithm, you take the 2D Fourier transform, and then you do the interpolation here, and then take the 3D inverse Fourier transform. Okay, so one last thing that I want to discuss is the resolutions that we end up with, range and cross-range resolution. We haven't derived this in the SAR lecture, in the SAR video, so I thought maybe I should do it here. It's easier to do it now because now you have the K space to work with, right? Okay, so we saw that in K space, we have Kz here, and we have these semicircles or circles, I guess, spheres. And this ranges from kt minimum to kt maximum, right? So this is the data that you've measured, basically. It lies in this space inside this region, right? And the way it's arranged is that it's equally spaced in X and Y, right? Okay, I'm not going to go through that again. Hopefully that makes sense by now. Okay, so this is the space where it is. We can make one other approximation here. So, if I have an antenna, my SAR, the element pattern of my antenna, let's say it has some beam width. Let's say you choose the 3 dB beam width, 10 dB beam width, and that has a beam width of theta b, right? So what does that mean? That means that plane waves or k vectors, plane waves coming from beyond this cannot be don't enter the antenna, right? They don't interact with the antenna's beam. So if the k vector of an incoming plane wave is coming beyond this beam width, it is attenuated by the beam pattern, the directivity of the antenna, right? Whereas k vectors that are coming from within the beam width, they can interact with the antenna. So the antenna can actually quote unquote see them, right? So what that means is that in k space, if this is your beam width, theta b, right? So anything that you measure out here actually is nonsense. I mean, there's no information there really, because those k vectors your beam actually did not measure. So although in theory, yes, you have some data there, but that data should be heavily attenuated by the beam width of your antenna itself. So you can kind of ignore that, right? And then let's assume that, okay, this is K naught, where K naught is omega center divided by C. KT min is omega min divided by C. And KT max is omega max divided by C, right? Omega max, omega min are the lowest and highest frequency in radians per second. Okay. So now what we want to do actually is we want to form a uniform grid here, right? So what I would do is I say, okay, anyway, I can't reach this area, so that doesn't matter. So I can just form my interpolated data in this region. Yeah, I mean, it's not exactly drawn very well, but yeah, that's the idea. Oops. So beyond this region, there's not much useful information. So I can form my uniform resample. Obviously, you can't interpolate data out here or out here, right? Because it lies outside the measurement that you actually made. So you can only interpolate onto a uniform grid inside this sort of this donut shape. And the most convenient way to do that is to say, okay, outside this beam pattern, anyway, nothing is there. So I just use the stuff that's inside it and form a rectangular grid in there and interpolate onto that grid, and then use a 3D FFT. That's something to keep in mind. In the next video, we'll actually go through the code of how this is done. So then that'll make more sense to you, but I just wanted to mention that. Okay. Now when you do this, basically, this is the maximum extent in Kx and Ky that you're measuring, right? And this is approximately 2k naught sine theta b divided by 2. And the maximum extent in Kz that you're measuring is 2 times omega bandwidth divided by C, right? It's the difference between KT min and KT max. Okay. So once you have the K space extents, you can find the resolution, which is again from Fourier theory. The resolution in X and Y is just 2 pi divided by this factor, 2k naught sine theta b divided by 2. And that is approximately lambda center frequency, or the center wavelength of the center frequency, divided by 4 times sine theta b divided by 2. And the resolution in Z is 2 pi divided by this value, 2 omega bandwidth divided by C. And that is C over 2 times the bandwidth. So this is the same as FMCW radars, right? Which is what we saw earlier, the range resolution, or resolution in Z. And this is actually the same as the resolution for synthetic aperture radars, SAR. Okay, almost coming to an end. The last thing I want to mention is that it's interesting to note that the resolution in X and Y is independent. Independent of what? It's independent of the array size, right? So unlike a lens, when I have a lens, the resolution depends on the size of the lens. If I have a small lens, the resolution is much lower. Whereas a large lens, the resolution is higher, right? Why is this the case, that it's independent of array size? That's kind of an interesting thing to note. And intuitively, it's because, let's say I have my synthetic aperture is like this. These are the beam widths. They're overlapping like that, right? Now, when I'm close by, let's say the target is somewhere here, right? I'm only, you're only seen by an array that's this size. These elements actually don't see anything. They don't see your target, right? Whereas when I'm out here, now all of these beams are interacting with it. So then the size of my array becomes like that, effective size. So because of that, when you're close by, the aperture size that's actually seeing the target is small. Whereas when you're far away, the aperture size becomes larger. So effectively the resolution remains constant. Of course, at the end of the day, your aperture is physically limited. So if you go very far away, then the resolution starts dropping, just like a regular lens with distance. Not with distance, with distance. But when you're close by, it's independent of the distance when you're in the near field of the entire synthetic aperture. So that's one counterintuitive kind of feature of SAR. Another one is that it's interesting to note that the beam width is inversely proportional to the resolution. So what does that mean? Typically for phased arrays, for example, the resolution, if you have a narrower beam, then the resolution is smaller, right? Then delta xy is lower. So in phased arrays, delta x comma y is proportional to theta b, the beam width of the entire array. Whereas in our case, it's inversely proportional to the beam width. Right, but this is not the beam width of the array. This is the beam width of each antenna. And again, the intuitive reason is the same. So if I have a very narrow beam array, let's say my beams are like this, right? Then a target placed here is only overlapping with one beam, and only one beam is able to see it. Whereas if I had a very wide beam array, like that, a wide beam antenna, now that same target is seen by these three antennas. So the resolution becomes higher, better. And that's why in synthetic aperture, you really want a very wide beam antenna. You don't want something very narrow that can illuminate the entire target basically from each position. So anyway, that's, if you're a SAR expert, you already know that. But if you don't, then that's kind of an interesting feature. Okay. So with that, I'd like to end this. In the next video, what I will do is I'll show you the MATLAB code rundown of implementing this algorithm. We'll also use a lot of experimental data that I've collected at W band, so at 80 gigahertz. And we'll look at some code results from that. Okay, thank you.